Okay, let's start class. So last time we started the non-parametric regression, and we talk about the global model, like the polynomial regressions. And then we know it's not that flexible and it's parametric. We have to predetermine some parametric model for that, which may not be feasible and not convenient for the practice, right? So what we need is a more flexible non-parametric model, okay? So without assuming the underlying model is a cubic model, linear model, quadratic model, so on, okay? So we talk about the piecewise polynomials, and then so that's the regression splines, okay, that belongs to, and also the B splines belongs to the regression splines. And then we talk about natural splines. So the difference between B spline and natural spline is that the natural spline is almost the same as B spline. The only difference is it it's outside the boundary of the data. It goes linear way. It does not go nonlinear way. So that can relieve some of the called the boundary effect problem. Okay, so and the good thing for this uh, remove the nonlinear effect, only go with linear outside the boundary, is that it actually frees 4 degrees of freedom. So that if we specify the model by the same degrees of freedom, using the natural spline give us more internal knots, so that the internal fittings, so that within the data range, our fitted model will be more flexible. Okay, so that's the natural spline. So you can see the basis looks essentially very close for the B-spline basis and natural spline basis. Okay, so this is the fit for the old phase 4 Geisel example. And you can see we both use the 10 degrees of freedom. Okay, but here you can see for the 10 degrees of freedom, you can see here in the B splines, this is almost linear, but in the natural splines, you can see some curvatures because it freed 2 degrees of freedom on each side. So you can see it goes linear. So that give us 4 extra internal knots placed in the natural spline. So how to use the natural spline and the B spline in the linear regression model, in the regression model. It's so you can see through this. So to use a natural spline is what? So that's just natural spline, what we call it is just the basis. It's a basis. So there is a term in statistics called the basis expansion. Okay, so what does that mean? Basis expansion is not a new idea. It's just you give me the x, right? I just created some new variables based on the x that you have. Okay, so and that basis may not be linear, may be non-linear of x. And that's exactly what natural spline, B-spline does. So what we do is we first use the NS. This eruption, that's the X. That's the original X. So for eruption, that is the X. Okay? And the waiting time is the Y. But when you have an NS of X, then we are actually not using X, but using what? Using the natural spline basis of X. Okay? And with 10 degrees of freedom. Okay, so what it means is that you can see here, it's actually creating this type of basis. So if it's X, what it will be? If it's X, then it's just a linear line. It's just a line. Oh, yeah, it's just a line, straight line. But it's not. It's a local basis. You see that? For these bases, like we have the on the leftmost part, you can see this part. So this is a local base, only non-zero when the when the eruption time is between 0 to, let's say, 15. Okay, the next one is the orange dash line. That's the basis. So from 0 to maybe 22, I don't know, close to that, right? So it's only if non-zero within a local area. And also it's non-linear. You can see it's not a straight line, it's a curve, right? So this is the B-spline basis. And of course here I'm showing the B-spline and natural spline basis. These are the cubic B-spline and the natural spline basis. So each basis is a cubic function, okay? And we can change that. We can change that to quadratic basis, B-spline, quadratic basis for natural spline. That's fine. And we can change to quartic and so on, okay? So that is available. So in order to specify the degree, let me see where, uh, yeah, here you can specify there's an option called a degree. If you said 1, that's just a linear B-spline basis, okay? And you can specify the knots location by yourself. Okay, so this is fitting a nonlinear model using the B-spline basis, or using the natural spline basis. Okay, you can also fit using the B-spline basis. Okay, so that's how we fit a nonlinear curve using a linear model. Look, what function did I use? Lm. Lm is a function in the R is doing what? Linear model. And you may ask, how we if using a linear model approach to fit nonlinear curve? So that's exactly the point. The point is what? The point is you can use the linear model to fit a nonlinear curve if you are not using that directly. You are not using that variable directly. You are using a nonlinear basis of that variable. Then, even though you use the linear model, the fitted model is still nonlinear. Do you see my point? So let me just repeat it again. So this is still considered a linear model because I use Lm. That's a linear model function in R. So it's just fitting a linear model. But the output of this model is actually nonlinear. The reason is that although this is a linear model procedure, but the x, we are not using the x. Usually the Lm, we have the response tilde x. Then this is a linear model. That's true. But now we're not doing the regression on the s or on the x, but on what? On the natural spline basis of x. You see that? Then that model, although fitted still by linear model, it's a nonlinear model because the basis is not linear, it's nonlinear. Okay, so that's the what we and then we talk about the smoothing spline. So smoothing spline is the objective function is to minimize that. Okay, we've already talked about what is the first term. That's measuring how good the model fits the data. The second term is the penalty that penalizes the model complexity through the curvatures, because that's the integration on the domain of x with the square of the second order derivatives. Okay, so in that way, if this model f is linear, there's no penalty. But if it's nonlinear, there's a penalty. Okay. So the model itself, the objective function is very is on a functional space, seems to be a very complicated solution, but actually it turns out to be a very simple closed form solution. It's just the natural spline. But natural spline on what? On what knots? On with the knots at all the unique value of x. So that's amazing. Why? Because then we remove the subjectiveness of selecting the knots. So that's actually one of the criticism for the regression splines. For the regression splines, you have to set what is the location of the knots. And you have to choose how many knots you are using. The number of knots you have to choose, and the location of knots you have to choose. Now all these removed. So the subjectiveness has been removed through the smoothing spline. The smoothing spline is very simple, says we assigned knots at each unique value of x. And that's the number of knots we have. So it's entirely data adaptive based on the data. So no subjectiveness. Okay, then you may ask, then that will have lots of knots, right? Think about you have 1,000 data points. That means if they are all different, you will have 1,000 knots. That's too much, right? So that leads to overfitting, but no problem. Why? Because we have a lambda here. The lambda is the tuning parameter. Remember, when the lambda is large, that means we have more penalty on the curvatures. So the model the final model will be close to a straight line, will be simpler because we have a large penalty on that. However, if the lambda is small, that means what? We have less penalty on the complexity of the model. So that encourages the model to be more complicated. Okay, so you can see the model will be overfitting or underfitting or right fitting. It all depends on what? Depends on one number, one value. That value is determined through the lambda. So lambda is the tuning knob. We can tune its value to make us a good model. Okay, so how do we tune the lambda? Go back to the model assessment. We can use cross-validation. Remember, cross-validation. And cross-validation can be computationally intensive, but no problem, because this is a linear fitting model, because the y hat can be written as a projection matrix times y. So for the linear fitting model, we have a shortcut for getting the out of leave one out cross-validation error. That's just fitting the model once using all the data points. And the leave one out cross-validation error is calculated in these ways. So you can see in this model, we use the f hat using all the data points, not leaving any data points out. And then we yi minus the fitted value divided by 1 minus SII. SII is the i's diagonal elements of S. Take the square, take the summation, take the average. That's it. That's the lever knot. So you can see there's a shortcut. We don't need to fit the model n times, just once. But that's still not good enough. Why? Because what is the dimension of the S matrix? S is a projection matrix, right? So if the sample size is n, the dimension of S is by what? M by n. And the dimension of the y is a column vector, that's m by 1. Okay, this is m by n. This is m by n. So think about if we have n equals to 1,000. So what is dimension of the S? That's 1,000 by 1,000. That's a large matrix. We have 1 million numbers in that matrix because it's a 1,000 times 1,000, right? If we have 10,000, that will be 100 million numbers in that matrix. That's a lot. right? So you can see that actually is to compute S is a bottleneck for the computational algorithm. Okay, so what we can do is there are efficient algorithms that can let us find out that without getting all the S, we only need to get to the diagonal elements of the S. Okay, so what we can further simplify is that we can use GCV, that's the generalized cross-validation. That approximates this. So, so this and this are approximately the same. Approximately the same. So this is exactly equals to leave or not cross-validation. This is exactly equals to, but this one is approximately equals to the leave or not cross-validation. But the good thing for this one is it's very simple. It's just replacing the SII by the average of the S, diagonal elements of S. So which is the trace of S divided by N. Trace is the summation of all the diagonal elements. So this is much faster to compute. Okay, so this is the advantage of using the GC in practice, especially if you have a big data set. So now let's see. This is the battery voltage drop example again. So I use the smoothing spline. In the R, there's a package called the R splines. If you use called the splines, okay, you download that and install on your in your R, open that, then you can just use the main function called the smooth.spline. It fits the smoothing splines. Okay, so this is the first term is the X, that's the time. The second term is the Y. And CV equals to F. F means false. CV means cross-validation, true or false. False. False means then it will, by default, it will do the generalized cross-validation. So instead of doing the cross-validation, it used the GCV to select the lambda. Okay, so if it's F, it used the GCV to select the lambda. So you can see the optimal degree of freedom is 11.24. So you may ask, what is that degree of freedom? Remember, we have, where is it? Yeah, so the effective degree of freedom of a smoothing spline is what? Is the trace of the S lambda. So what is S? S is a projection matrix, which is a function of lambda. So we put lambda in the subscript. It's not S times lambda, it's the S itself. But S itself is a function of lambda. Okay, so that's the trace of the S. That's the effective degree of freedom. That means how complicated the model is. This is a good measure of the complexity of a model. Okay, so so you can see instead of showing the lambda, it shows the degree of freedom chosen by the GCV. So you can see when the degree of freedom is 11.24, it minimizes the GCV. So that's the optimal degree of freedom. Okay, and you can see that's the fitted smoothing spline. And when we use the degree of freedom is 30, more degrees of freedom. So we preset it. So you set the df equals to 30. That means preset the degree of freedom. Then you can see the fitted model is what? Is much more complicated. And that actually leads to overfitting. So it's not smooth. It changes by these, especially if you look at the top, you can see the curvatures. So it's affected by the noise of the data points. So as I said before, we are not estimating the Y, we are estimating the F. Remember, we talked about that. So a general assumption is Y equals to Fx plus some additive noise. So a good model is estimating the F. That's a good model. An overfitted model is not estimating F, but estimating Y. Because Y, there's no way to estimate Y. Why? The reason is because the y is a corrected version of f with some random error. Random, what do we mean random? Random means that we cannot take a guess. It's pure random. If you have a new data point, we have no idea about what epsilon is. Okay, so this, a good model should estimate f. That's estimating the f, and this is overfitting. Okay, so this is the SAS code. I will just skip that. If you want to use SAS to get the non-parametric regression, you can take a look. And SAS output, GCV. So here, I just want to mention one thing. When you use different software, like R and SAS, there is a common problem, potential problem, okay, between using different software. Like here, the optimal model with that minimize the GCV is 11.24 in the R, right? But here, we can also do that using the GCV in the SAS. Okay, let's see what is the optimal degrees of freedom. So the optimal degrees of freedom, let me see, is the here. This is 11.24. This is the where? Yeah, 10.24. This is the 10.24. Why? You can see here we have these degrees of freedom, and then we have 1 degree of freedom from the linear part. Let me exclude where it, yeah, yeah, this is I didn't see where's the 11 10 point. Anyway, so my point is in the R, actually when they count for the degrees of freedom, it actually removes 1 degree of freedom by removing the linear trend. Okay, so when you compare the results from 2 different softwares, sometimes you have to be very careful because in the SAS, it has 1 less degree of freedom because it removed the linear trend. So that's why when you use different softwares, you have to be very careful. Like here, it's 9.23 something. That's the optimal. But here we have the 11. And the reason is because it's actually removing didn't consider the intercept as well as the linear part. So this degree of freedom is entirely about the nonlinear part by removing the linear trend. Okay, so that's why when we do the GCV, you will see, oh, this is different from the R. It's not different. It's actually almost the same. The reason is because it removes the linear part, which has 1 degree of freedom for the intercept, 1 degree of freedom for the linear. If we add these 2 back, so that will be 11.23 something, which is very close to 11.24 in the R. Okay, so that's the information for the using different softwares. You need to be careful. Okay, see. So we talk about the nonlinear smoother through the regression splines, through the smoothing splines. And also we can use some other nonlinear smoother, like this called the kernel smoother. Okay, so the kernel smoother is really using the weighted average. Okay, so like these are the data, the blue dots are the observed data points. We want to fit a nonlinear smoothed curve. So what should we do? So what we can do is, so like for when the x is x0, what is the fitted value? So it just gives you a neighborhood. So you can use the kernel smoothing. So it gives you a neighborhood. And also you can see in the plot that this neighborhood has a bell-shaped curve. And that's actually proportional to the weights. So for all the data points within that neighborhood, so these red dots are within the neighborhood. So the neighborhood is this. Okay. So I draw these two lines. That's the neighborhood. So within this neighborhood, like these points on the boundaries, these points are having very small weights. But when for these points very close to the center, very close to the x0, they have much higher weights. So the height of the yellow shaded area, the height of the yellow shaded region is proportional to the weights. So it's a weighted average. Okay, and all the points in the neighborhood, that's the red points, they have contributions. But close to the x0, more contribution. All far from the x0, no contribution, very small. But outside the range, outside the neighborhood, like this blue point, has no contribution at all. Okay, so then we can get the weighted average, which is here. And then we move to the next point. We find a new neighborhood, right? We get the weighted average, so we get the next. So we just plot these weighted average. So you can see the red curve is the kernel smoother fitted curve, which is smooth, and the green one is the true function from this simulation. Okay, so you can see we can use kernel smoother as an alternative. Okay. Okay, so this is an example for the old faithful example using the kernel smoothing. So for the kernel smoothing, there is a tuning parameter. It's not lambda, but what? But the neighborhood size. So the size of the neighborhood, that really matters. If we have a large neighborhood size, then it will be smoother. If we have a small neighborhood size, then it will be less smooth. Okay, so here you can see the neighborhood size is determined by the bandwidth, right? So when the bandwidth is small, you can see the fitted curve is very not smooth. But when we have a large one, it's smooth. Even larger, it's very smooth. Okay, so, and you may ask how to choose the bandwidth. We can do it through the cross-validation. Okay, and there is this function K-smooth is in the base package. You don't need to install any library. You can directly use that. But if you want to use some more comprehensive, more complicated kernel smoothing, like if you for this K-smoother, it just have a few options for the kernels. But for the curl smoother, it contains a very comprehensive options for the kernel to choose. Okay, so what is kernel? Kernel is the weighting function. So that weighting function here, you see that? That's the kernel we are talking about. So this kernel is a Gaussian kernel. Gaussian kernel means like it looks like a bell-shaped curve. But that's not the only option. We can have some different shape. Like we can have a square, right? So the weight can be a constant weight within the neighborhood, like that. Or we can have a triangle, right? So we can have different shapes of weight, kernel functions. Okay, so if you want to have a large option, then you can use the curve smooth. That's the package. Okay, that's another smoother is which we've already talked about is the local linear or local polynomial regression, and that's the example is the lowest smoother. We've already talked about that. Remember when we talk about the model estimation, I show you one example about the compliance against the improvement in a clinical study. Okay, so we use the Lowy smoother. So Lowy smoother basically very similar to the kernel smoother. It's a local approach. So first we choose the neighborhood. Then we are not doing the weighted average. We are actually fitting a line within the neighborhood and using the weights just like weighted average. So the weights can be a kernel weight. Okay, so so here we fitted a local linear regression using these weights, and we get the estimate at x0. Then we move to the new point. So that's the lowest smooth. Okay, so and this is the example for the revisit the old phase 4 example using the lowest smooth. And so you can see, so the tuning parameter is called a span. Okay, so span is the neighborhood size. When we have a small neighborhood size, you can see it's very complicated, the fitted curve. Have lots of curvatures, but when we have the span is 0.5, which is much larger neighborhood size, you can see it's very smooth. Okay, so this is the lowest smoother in the SAS, and this is the fitting from the SAS. Okay, any questions for the nonlinear smoother? So we talk about the global models, we talk about the regression splines, we talk about the smoothing spline, we talk about kernel smoother, we talk about the lowest smoothers. So we have lots of choice, right? There are some other approach. Okay, now if you don't have any question, we will talk about today's main material. So it's about the generalized additive model. So why we need to talk about nonlinear smoother? You will see that in a minute. Okay, so first question is why we need to talk about the generalized additive models, right? So traditionally we fit linear models. We are very familiar with that, right? This is a multiple linear regression model. So the good thing is it's simple and easy to interpret. Ideal for the linear effect, small sample size data. But the drawback is what? The drawback is in the real life, most of the time, the relationship between x and y is not linear. It's actually nonlinear. Is that right? So that actually caused the problem. Okay, so another approach is the multiple non-parametric model, which is very complicated. Y equals to fx plus epsilon. X means all the x. So this, a good example is like deep learning model, artificial neural network, and you will see like the tree models, like the random forest. So we have lots of machine learning algorithms, models falls into this non-parametric model. Okay, so the good things is it allows nonlinearities, all possible interactions covered. That's good. And ideal for the large M and small p. Why it's large M? We need to have, since the model is complicated, we need to have sufficient amount of information to fit the model. Does that make sense? Because the model is too complicated. We need sufficient amount of information. So we need a large sample size. While the p is small, when the p is large, this approach will have very well-known phenomenon called curse of dimensionality. Okay, I will explain in a minute. So the drawback is it's hard to interpret and unstable due to that curse of dimensionality. So what does that mean? That means, let me show you an example. In the high dimensional data, the data will become very, very sparse. Okay, that means the data points will be very far from each other if we have a high dimension. Okay, so what does that mean? Let's just start with simple. Okay, for one dimension, if we have 100 data points, okay, so think about just as a very simple case, we have from 0 to 1. That's only one dimension on a line. And I have 100 data points. So I can put them here. So we have a density, right? So now the question is, now if I have a two-dimensional space, so let's say it's a square with each side is 1, length is 1. So we have a square. How many data points we need to have to achieve the same density as 100 data points on one line? How much data points? Think about that. We need to have what? We need to have, since it's two dimension, so we need to have what? 100 to the power of what? 2. If we have that many data points, then we can have about the same density as one-dimensional case. Does that make sense? So if you think that's okay, that seems to be right. Now, what about 3 dimension? 3 dimension, we need to have not to the power of 2, but to the power of 3. Does that make sense? Okay, so some of you may not still, so what does that mean, density? So think about just one dimension. You have 100 data points. So what is the distance between one data point to its neighbor? It's 1 divided by 100. Is that right? So if we have 2 dimensions, if we have the 100 to the power of 2, you can easily see that we can still keep the same distance, 1 over 100. If we have 100 to the power of 2 data points, you can easily draw the lines or draw the points. If we have that many data points, and on the average, the distance from one point to its neighbor is just the 1 divided by 100, right? So it's, and 3 dimension, then it's to the 100 to the power of 3. Okay, now let's go beyond 3 dimension. That we cannot see, we can only imagine. Okay, it's not difficult to imagine. It's just if we go to the p dimension, then it will be the 100 to the power of p to get the same density. So that means what? That means to achieve the same density, the sample size goes exponentially fast. Okay, now what if we still have just 100 data points in p dimension? Then the result is what? The data points becomes more far from each other. Does that make sense? Even in the high dimension, we still just have 100 data points. Then the distance from 2 data points, even their neighbors, will become much larger than in low dimensions. I think that's still reasonable, right? And that's the curse of dimensionality. Says in high dimension, data points are very sparse. That means we cannot estimate the function well because of the sparsity of the data points. Because if in that region we just have one data point or no data point, how do we estimate the function in that region? Right? So that's why it's called the curse of the dimensionality. So curse of the dimensionality means that when we have large number of variables, the sample size should grow proportionally in terms of the power. Okay, so that means if we have 100 for one variable, then we have 100 to the power of 2 for 2 variables, and so on. So that usually works well. Okay, so this is further explanation for the curse of dimensionality, but I will just skip that. Okay, so what is GAN? So why we need to have a GAN? The GAN model, the generalized additive model, is actually somewhere between these traditional approach, traditional linear model, and the modernized multiple non-parametric models. It's somewhere between. And actually, it inherits the good things from both. Okay, first is, again, is much more flexible than the linear model. And you will see that in a minute, because it allows nonlinearities. And it also allows interactions in some ways, okay? And on the other side, it also highly interpretable. Okay, so unlike this one, it's very difficult to interpret, but the GAN model is very easy to interpret, and I will show you in a minute. And the third one is it actually avoids curse of dimensionalities. If we have high dimensional data, no problem. GAN can avoid curse of dimensionality. I will show you in a minute why it can avoid. Okay, so that's why we need to learn the GAN. It's somewhere between, it's more flexible than the linear model, but it has almost the same interpretation power to interpret the models. Okay, so the GAN model looks like that. So this is the simplest GAN model. Okay, I'm just start with the simplest form, regression. Okay, so the y can be modeled by an intercept plus a function of x1, a function of x2 to a function of xp plus additive noise. Okay, so here what is f? F can be arbitrary functions estimated from the data. So f can be linear and can be nonlinear. So then you know that why we need to talk about nonlinear smoother at first. Because to estimate those f, we can use nonlinear smoother that we just learned. So we can use smoothing splines or lower smoothers or something else to estimate this f. Okay, but f can be linear or can be nonlinear, can be step functions, can be so very flexible. Okay, so the choice of these f here, I'm just listing a few. F represent the arbitrary trend that can be estimated through some nonlinear smoother. In some case, additive form, the additive term may be known. So if we know, let's say, the relationship between x1 and y is linear, then we just enforce the f1 to be a linear model. Okay, if we don't know, we just leave it open. So for the local regression, we can use lower smoother, and we can do the splines with the fixed degrees of freedoms. We can use the splines with known knots and boundary knot locations. And sometimes we can use the harmonic term. What is harmonic term? It's like a sine, cosine function. So these are the periodic function. So sometimes we may use that. Why? Because let's say if the y is the cell volume of some product like a grape. Okay, so the y is the price of the grape or the cell volume. So we know that grape is a seasonal item. So the cell volume changes with the seasons, right? Like right now in the fall, the cell volume should be high, but in the spring it should be very low, and so on. So we have some seasonal periodic effects. So sometimes we can use the harmonic terms for the f to include those seasonal effects and so on. But in general, the degrees of smoothness can be chosen through the cross-validation or through the GCV that we talk about, right? So we can easily do that. Okay, so how to fit a generalized additive model? Okay, we won't talk about the details. I'm just giving you some brief idea. So the procedure that we use to fitting the generalized linear model is very smart, very, very clever. That's called backfitting. So the backfitting is what? So here is the algorithm. Okay, you can take a look for this, but let me just explain that in simple ways. Let's say we have 2x. Okay, we have x1, we have x2. Okay, so that's a very simple, and we have the response y. So y equals to, let's say, the beta 0. Let's just remove the beta 0 because we can easily add the intercept. That's no problem. Or we can remove the intercept by centering the response. If we subtract the response value by its mean, then the intercept term is basically gone, right? So let's just think about the simple case so you get the idea. Y equals to f x1, only two x variables, plus g x2 plus epsilon. Okay, so that's x1. Okay, so how do we estimate the f and g? In the backfitting, okay, first we start with some initial value. Okay, so let's say we first initialize the f and the g to, let's say, constant 0. That's fine. Okay, but you can use some others. That's no problem. But what we can do is first we find there's a very important concept called partial residue. So what is partial residue? Let's say first, let's say we want to estimate f. So then to estimate f, we use the partial residue for the f. What is partial residue? That's y minus gx2. So after that, we get the value. That's the partial residue. Why it's called partial? Because the residual should be what? Y minus f and g. But here, we are not minus f. We are just minus g. So y minus g, that's partial residual for f. So we use that as the new response. Let's call it z. And to do the regression on the, to do the nonlinear smoother on the f using the x1. Is that clear? So this equals to z as the partial residual. And we use this partial residual as the response to fit a nonlinear smoother, let's say smoothing spline, on the x1. Then we get an estimate of f. Is that clear? So now we have the new f. We updated the f to be this f. Okay, then how do we estimate the g? Same thing. Well, now we have the partial residue for the g. That's the y minus f x 1. Is that clear? So this is the partial residual to estimate the g. Okay, now let's say this is the new response z. Okay, now this time I'm fitting a nonlinear smoother on the x2 to estimate the function g. Is that clear? So then we estimate the g and then updated the g. And then we go back to estimated f again. Then estimate the g, estimate the f, estimate the g, doing that. And you may ask, when we should stop? So you can see when we do these estimations, we will compare our estimated values. Okay, if the f and g didn't change much, of course, we can set some tolerance of the algorithm. If the change of the f and g are smaller than a predefined amount, then we will say, okay, the algorithm converges. Then we will just stop. So usually the convergence is very quick. Just by a few rounds, it will converge. So that's the backfitting. Okay, now go back to the curse of dimensionalities. So why I said before that the GAM avoids the curse of dimensionality. Why? Why the generalized additive model avoids the curse of dimensionality? I think it's not difficult to see if you understand this algorithm. For this algorithm, we estimated all these f's. We estimated f1, f2, f3 as what? as a univariate nonlinear smoother, only one x at a time. So we estimated f for each variable, each one variable at a time. So we don't involve the high dimensional estimation. So that's why the GAN algorithm does not suffer from the curse of dimensionality. So that's very important because we have to be realistic. This is a big data age. Most of the time, if you go to the industries, like you go to the Walmart, they have some sales data. Okay? Think about how many items do they have? How many categories do they have? How many variables do they have? I would say in reality, the number of X can easily go beyond 10,000. If you don't have these like a GAN approach, smart approach to avoid the curse of dimensionality, the model fitting will be first very computationally intensive, very slow. It may take hours, days, weeks to get a model fitted. And the second is it's very difficult to interpret. And the third is it may easily lead to overfitting, right? But for using the GAN, it does not suffer from the curse of dimensionality. When do the fitting, it's a univariate dimension, one dimension at a time, fit one F at a time. So it's very fast, much faster, right? And also it's highly interpretable. So that's why I think GAN is probably one of the best model approach in statistics. Yeah, so that is very different from the machine learning algorithms in the computer science, which here is computationally efficient and also easy to interpret, and also very flexible because it can also fit nonlinear effects and the interaction. You will see that in a minute. Okay, so now this slide goes to the generalized part. So GAN means generalized additive model, right? Why we call it generalized? The G stands for generalized, means it's just like generalized linear model. Okay, for the generalized linear model, we are not modeling the we are not modeling the y directly. We are having a link function. Okay, so here we can do the logistic model using the GAN. And with the logit link, we can do the probit model using the GAN. We can use the Poisson model by using the log link function. Okay, so it's very general. It's not just for the linear regression, like assuming the normal, normally distributed for the y. We can have all types of response variables, like binaries, count data, these. And also, we can have various types of nonlinear terms in the GAN. Okay, so let's say, suppose we have 4 variables. X, Z, W are quantitative variables, and the V is a qualitative variables with D levels. Okay, think about V is like a season. So we have 4 levels: spring, summer, fall, and winter. Okay, like that. X, Z, Y, these are the quantitative. Okay, so now you can see we can fit a GAN model like that. And this has a name called a semi-parametric model. So semi-parametric model means what? Part of it are nonlinear, are non-parametric model. Part of the model are parametric model. Combined together, semi-parametric model. It's somewhere between. Okay, now let's see. What is the parametric part? The parametric part is the linear relationship between the x and y, because we enforce the effect of x is linear. That's x times beta. So that's the parametric part. What is the non-parametric part? Non-parametric part is, for this one, we are actually modeling the qualitative variable v, okay, through its main effect. We do not assume these levels have some forms, okay? Plus, we also have the fz, that's the modeled effect of z through a very flexible f. So we do not assume the f is linear or nonlinear. Is that clear? So that's why it's called a semi-parametric. So these two are non-parametric, and these x is parametric. So combined together, the model is semi-parametric. So this GAM is a very good approach to add some subjective knowledge in the modeling. Think about, you have a data set, you know that based on some previous findings by other researchers, we know that x and y should be linear. Then you just enforce that to be linear. That's the semi-parametric model, okay? And this example shows an interaction between the v and the z, okay? And so the first term, fx, that's the main effect for the x. What does main effect mean? Main effect means x impact on the y without any other variables. So x has its own effect on the y, okay? And this is an interaction effect between the v and z. Why? Because you can see this term has d levels, and v has a qualitative variable with d. And for each level, it's a function related to the z. So this is an interaction between the v and the z. Okay? So the reason I put this example here is that interaction, I noticed that some people only think about interaction exist between two numeric variables. That's not right. Interaction can exist between two qualitative variables. Interaction can exist between one qualitative and one quantitative variables. And of course, interaction can exist in between two quantitative variables. So this is just one example that have the interaction between one qualitative, one quantitative variables. Okay, and this is a non-parametric GAN model that includes the main effect of x and interaction effect between z and w. Okay, so you can see through these examples, you can see the GAN model is very flexible. It includes nonlinearities. It includes the semi-parametric model that includes some parametric terms. It allows to have those interactions. So it's very flexible, but on the other hand, it's also easy to interpret. You will see some examples in a minute. Okay, so how do we use GAN in R? There were two excellent packages, but that's not only two. There were actually a few more. But here I'm just focusing on these two package. One is the MGCV package. MGCV's package is a very standard R package that has a main function called the GAM function. And there is another package called the GAM package. And the main function is also called GAM. So when you use these package, just be careful. Okay, you need to attach one library, open one library at a time. And if you want to use the other one, make sure you close that library, because otherwise you don't know the GAN you are using is from the MGCV or the GAN package. Okay, so what are the difference between these two packages? So the MGCV package has the GAN function, only allows using the smoothing splines. it only allows smoothing splines to do the nonlinear fittings. Okay, so you can see that's limited just by that method. But the good thing is that it will automatically using the cross-validation. Or you can, of course, manually choosing that with the optimal degrees of freedom. So in other words, if you have a data set, you don't want to spend too much time to tune the models. You just want to have a quick fit, but a very good fit. Use the MGCV package using the GAN function in that model. Then you can use smoothing spline. It will automatically choose the optimal smoothness for each term through the generalized cross-validation approach. So you don't need to worry about that. It will choose it for you, so it's easy to use. Okay, so for the GAN function in the GAN package, it has more flexibility to choose the nonlinear smoother. It allows the lowest smoother. It also allows the smoothing splines. And actually, if you want to use some other smoother, it can also be added with some appropriate interface functions. Okay, so very flexible if you want to try different smooth and nonlinear smoother. So, but to choose the optimal smoothness, it does not allow the automatic chosen. So the user has to choose by itself. Okay, so for the convenience, this is more convenient, but for the flexibility, this is more flexible. Okay, and then either one, we can, after fitting the model, we can use the ANOVA function to to compare the models, and I will show you some examples. Okay, start with the first one. Before this example, any questions so far? Okay, so for the first one, that's our wheat yield data. So we have the response is the yield of wheat. And the predictors, we have 9 predictors. Year as a surrogate for the improvement of the crop varieties. And rain 0, 1, 2, 3. These are 4 different variables related to the rain amount perspective. And the temperature 1, 2, 3, 4 are related to the 4 variables for different temperature measurement. So we only have, so each observation is a year. Okay, so we only have 33 years observations. Okay, we have only 33 observations. One observation means a year. We have 9 possible predictors. So consider this the sample size and the variable size. This is a very high dimensional data. Why? Because we only have 33 observations, but we have 9 variables. So before we fit in the GAN, usually the first thing is let's just fit some linear model. Why? Because to use this initial step, fitting the linear model, we can filter away those irrelevant variables first. That makes sense? Because we start with simple, so we can use stepwise selection to remove those irrelevant variables so that we can fit the GAN model better. So here, I'm first fitting the multiple linear regression using all the data points. Then start from that, I use step AIC to do the stepwise selection. And I set the K equals to that. Okay, this is actually doing the BIC, Bayesian information criteria. Remember the BIC and AI. Oh, remember for the AIC, that's the -2 log likelihood. It has a name called deviance plus 2 times the number of parameters. But for the BIC, the first is the same, -2 log uh, likelihood plus not 2 times d. D is the number of parameters in the model, but the log n, the log of the sample size times the number of parameters. So you can see this is log n, this is the 2. They are different. So BIC basically put more penalty on the model complexity because log n is usually bigger than 2, right? Just a small sample size can be much bigger than 2. So that means, so here I use BIC. The reason is that if I use BIC, I put more penalty on here. That means what? The BIC usually selects what? Simpler model than the AIC. Okay, so I want to select just fewer variables. So that's why I set the K not equals to 2, but this one. So this is log n. This is n row of our data. So that means this is the sample size, log of n. That's this one. That's the K. Okay. Okay. So you can see the model looks like that. So after using the stepwise, we have only 4 variables selected. Temp 4, range 0, range 2, and year. Okay, so these 4, the temperature, the year is highly significant. This one is significant, but these 2 are marginally significant. Okay, so that's the results. Now we can start with our GAN model now. So the initial reflection is that we got 4 even with the more stringent BIC penalty. And then, but anyway, we found these 4 variables. Okay, so now let's start with the GAN. So we use the GAN library. Okay, so we have these libraries and we fit the GAN. So in the GAN, we have the S. What does S mean? S means smoothing splines. Okay, so what if I want to just fit a linear model on the temperature 4, temp 4? So if you want to just fit a linear model on the temp 4, so that will become a semi-parametric model. For the semi-parametric model, you don't need to have these S and parentheses. Remove that. Just use the temp itself. Remove the S and parentheses. Then that means you fit the GAN model with temperature is temp 4 is linear function plus a smooth spline fitting for the range 0, smoothing spline fit for the range 2, smoothing spline you fit it for the year effect. Okay, so that's how, and you can see here how to interpret. So we can interpret through the component plot, just using the plot for that model object with the standard error is true. So it will show you the standard error. Residual also true. Okay, now let's see what does that looks like. So this is the component plot for the model. Okay, so first thing is, what are these points? These are not observed points because you can see some of them are negative. Remember what is the response variable? Response variable is the yield, right? So how can the yield be negative? So these points are what? Remember in the backfitting, we have a very important concept that's called partial residual. So these points are showing the partial residual. Okay? So these are not real data points. These are the partial residual points. Okay, and this is the fitted curve on that part using that partial residuals. So you can see here for these, you can see there's a dot line around the fitted curve. These dot lines are the standard errors. Okay, and So which variable is most important? Just by looking at that. So first, I tell you there's a way to help you to see which is more important. You draw a horizontal line at constant 0. So this is probably a good line for the constant 0. If the standard error band covers most of the regions for the constant 0, that means this variable is not that important. Does that make sense? Because it's around 0. So what important? So, but if we can see a very clear trend, and that trend is away from that, then it shows the importance. So here, I would say the year is the most important, because if we draw a line, you can see we can easily see there's a trend, increasing trend. And that, as I said at the beginning, year is used as a surrogate for the improvement in the crop varieties, because the scientists designed the crop varieties, try to improve the yields, right? But also interesting thing is what? The interesting, if you take a look, we have a stop between these, right? And this is the hour data. So you can see what are these years? 1942, maybe 41, 42 to 1950. So these are the during the World War II and the post-World War II. So you can see there is a pause of improvement during the World War II and right after the World War II. And that also makes sense because at that time, these scientific research are not the focus, right? So you can easily see the interpret the models through this component plot. And that you cannot see from the artificial neural network, and which we will talk about later. And also, it's more flexible than the linear regressions. Okay. Okay. So I think we've already talked about that. Okay. So the inference. Now we want to talk about the inference. So for the inference, let's see here, we do the summary for the GAN model. You can see here, first is number of local scoring iteration. So that's the number of iterations for the backfitting. Only 2 iterations is enough. So 2 iteration, what does that mean? In the backfitting, let's say, so for that whole cycle, that's called 1 iteration. So 1 cycle includes fitting the F for all the X variables. Doing that as 1 cycle, that's 1 iteration. So we only need to have 2 cycles, then it converges. So you can see it converges very quickly. Okay, and this is the degrees of freedom for the non-parametric effects. So here we have the first column is the degree of freedom. That's the degree of freedom for the linear effects. Okay, so the second column is the nonlinear effects. Okay, and this is the nonlinear effects f, and this is the p-value. So you can see in the GAN function, we use the GAN function. It does not automatically choose the degree of freedom. It used by default, it sets the degree of freedom is 3. So 3 is the default degree of freedom for each term. So that's why you see 3 degrees of freedom are for each term. And that's for the nonlinear part. For the linear part, we have 1 degree of freedom for each term. And these are the p-values to show the significance. And also this test shows what? Shows the year is a significant, right? Besides the year, the second one would be temp 4. Or no, will be range 0. Okay, so that's the each individual to see if the non-parametric is significant or not. Okay, so can we get to the same place with the GLMs using the natural spline and the B splines? Yes, we can do that. We can approach similar results like that. So what we can do is, you see, now I'm using the linear model, the yield, but now this time yield is regressing on what? Natural splines with temp degrees of freedom 3, rain, natural splines on the rains, plus natural splines on rain 2, plus natural spline on the year, all with degrees of freedom 3. Okay, so then we can do a term plot. So you can see it looks like similar. Compare this one with this one, very similar. And you may say, then why we need to do the GAN? There's a very different thing between this model and this model and this. Okay, so what's the difference? The difference is that think about using this approach, we fit each term simultaneously. So this approach suffers from curse of dimensionality. But that GAN model does not. Why? GAN model fit each term individually. So it avoids curse of dimensionality. In other words, if we have large number of variables, this one doesn't work. This approach does not work. It will be crashed. If we have more variables than the sample size, it's not estimable. There will be error message come. Okay, so that's the main difference. But if it allows to do that, then we may get similar results. Okay, so that's the main difference. Okay, so final remarks on the Iowa wheat example. So is that we know that year is the most important, and now clear that the term rain 2 is not significant. How do we know the rain 2 is not significant? I didn't explain, but if you draw a line for the constant 0, it's probably here. That's 0, okay? You can see the constant 0 is within the standard error band. So that means what? That means the fitted curve is not significantly different from 0. So that's why it's not significant. And also you can see the p-value. If you look at the p-value for the range 2, not significant at all, right? Go with the range 2 here, not significant at all. So both approach shows the range 2 is nothing, okay? Only temp 4 and range 0 needs to be reassessed if we have more data points. But obviously the year is the most dominant. So that's the final remarks. Oh, we don't have time to go over the rest of the 3. So I will go over the rest of the 3 examples quickly next time. So I will assign the homework 4. So I think we will have 4 or 5 homeworks this semester. So homework 4 will probably be maybe the last or the second to last homework. Then we will start our midterm group presentation. So I will post the announcement either the end of this week or early next week and talk about that. So we will, you may start to find your teammate usually we allow two students, 3 students, 4 students, up to 4, no more than 4. And 2, 3, or 4, these are good numbers to work as a team and work on a data set. You can use your research data if you have, but if you don't have that, I will provide you some source for the data set that you can choose one of them and as your working data set. So I will talk more details and send you the announcement. Any questions before we start? Okay, so let's stop here.